So, to find an inverse, we have to remember where I put my pen. Did I put it back in here? All right, well, we're changing to blue because I don't know where I put my black pen. I just set it down. Anywho, all right, moving on. So to find an inverse, step one, we're going to change f of x or g of x, etc., okay, to y. Okay? Then we will swap x and y variables. And then we'll solve. Once swapping, we'll now solve for y. Okay, right? And then once we've done that, we will rename y as f inverse of x. Okay? Or of course, g inverse of x, etc., depending on, whatever the previous name was. Okay? So one thing I want to point out, right, when you see that little to the negative 1, right, you might think, oh, this is like to the negative 1 power. Okay? You might think it's like an exponent there, okay, that to the negative 1. But it does not mean power, right? It means inverse. All right. Yes, we do use negative 1 exponent, okay? That does mean something that has a different meaning than this. But this does not mean 1 over f of x. So this does not equal 1 over f of x. Okay, it's not the same thing. An inverse is not the same thing as a reciprocal. Okay? 1 over f of x does equal f of x to the negative 1, like that. Okay? But f with the negative 1 there of x, that means an inverse. And they're two different things. Okay? Sometimes they're the same thing, but that's in a very special case, or a very specific case. Okay? So let's go about finding what an inverse is. Okay? Let's go about finding an inverse, and then we'll kind of talk more about like what is an inverse, what it does, what the purpose is, and stuff like that. So let's find the inverse of the given functions. Okay. And we'll do one here. We'll say h of x equals 2x plus 6. Start with an easy one here. Okay. So h of x equals 2x plus 6, right? We're supposed to change that h of x to be a y. Swap the x and y's. Okay, and just like literally where you have a y, now make it an x. Where you have an x, now make it a y. And now we'll get the y by itself. So we'll solve by subtracting x on both sides here. Get 2y equals x minus 6. Okay. And then divide both sides by 2. So we get y equals x minus 6 over 2. Okay. Which you can leave that way if you want to. All right, but that's kind of, like a weird form. Okay. We can rewrite this instead. We can break up a numerator over a denominator here, so we can make it x over 2 minus 6 over 2. Okay, so this is a property, right, that we can do. Just like if you have two fractions that have, when you have two fractions that have common denominators, you can combine them together with addition or subtraction, right? You can combine those to a single fraction. Likewise, you can go backwards, right? If you have a single fraction, you can then break them up over a common denominator of the 2 there. And then we could simplify this maybe one more way by saying that's 1/2 x minus 3. Okay, and so we can say then that h inverse of x is 1/2 x minus 3. Okay. Okay. So what is an inverse, right? An inverse is a concept that we use in math in a couple different ways. So for example, you use the concept of inverse when you solve equations, right? If you see addition in an equation, then you know that we're going to use subtraction to cancel it out, right? Or if you see multiplication in an equation, you know that you use division to cancel it out, right? And the reason for that is because addition and subtraction are inverses of each other. They kind of cancel each other out, okay? And likewise, multiplication and division are also inverse operations. They cancel each other out, right? They result in an identity, right? If you have 3 and then you divide by 3, you have 3 times x, and you divide both sides by 3, right? The 3 divided by the 3, they cancel out, right? Kind of thing. And so those are inverse operations because they kind of have this idea of canceling out. So likewise, later we'll see this same idea show up with inverses as well. This function and this function, they kind of cancel one another out, okay? And there's other ways that these are related too. But so far right now, those are just inverses, we'll see. Okay, that's the inverse. So let's try another one here. Okay. Okay, we'll say f of x equals the square root of 2x minus 3. Okay, square root of 2x minus 3. And so again, we'll change this up here and we'll make it, y equals the square root of 2x minus 3. Okay, and now what's our next step here to find the inverse? What should we do? Swap the x and y's, right? Exactly. So we have x equals the square root of 2y minus 3. And now what should we do? We need to solve for y, right? So what should be our next step in solving for y?
Square both sides.
Oh, yeah, yep, that's okay. Square both sides, that's fine. Yep, so square both sides, we get x squared equals 2y minus 3. Okay. Again, when you square in an equation, you can't pick and choose what you want to square, okay? You got to square the entire left-hand side and the entire right-hand side. So in this case, it's good. We have we have a square root for the entire right-hand side here. So if we square it, it's going to cancel out that entire square root. Okay, and now we can add the 3 over. So I'll go ahead and flip my equation around here, make it x squared. So 2y equals x squared plus 3. And then, again, an alternative way, you could think about dividing both sides by 2, or we could also multiply both sides by 1/2, and so we get y equals 1/2 x squared plus 3, like that. Excuse me, y equals 1/2 x squared plus 3, like that if you like. Which, if we distribute the 1/2 there, it would be 1/2 x squared plus 3 halves. Okay, if you like to have it all distributed out nice and neat. And so then that would be, that would be f inverse of x is equal to that 1/2 x squared plus 3 halves. Okay. So there would be our inverse. Oh yeah, question.
Do you want us to simplify all the way?
Not necessarily, no. Not necessarily, no. But again, should this show up like on a multiple choice kind of question, you need to be able to manipulate yours to be able to match what's the multiple choice too, right? So, and generally when it comes to multiple choice, the multiple choice answers are simplified as compared to, maybe like having the 1/2 outliers. Okay, same idea here, right? You see this like x minus 6 over 2, right? That's kind of funky looking, but then when we actually simplify, we get down to something that's like, 1/2 x minus 3, and it's like, that's a line, right? We can just graph that. The slope is 1/2, the y-intercept is -3. So it is helpful, and I would suggest simplifying. Okay. All right, now, I have a little bit more to be said about these two things, but I'm going to come back to that in a little bit here. Okay, just because I want to make sure, I want to make sure that I want to cover something else first, but we'll come back to that, okay? So, let's keep going here. All right, so let's also talk about how we can verify inverses as well. Okay, so verifying inverses. One way we can do that is, I guess, what I'll call like algebraically. Okay, we'll call that algebraically. And we'll say if f and g are inverses, then f of g of x equals x, and g of f of x also equals x. Okay? Both must be true. To verify inverses. Okay? Both must be true to verify inverses. So if you plug one function into another function and you simplify down to x, but then you do the reverse and you don't get x, those functions aren't inverses of each other. Okay? Only inverses have this occur. Okay? Only inverses do that. So if your inverse functions don't do that, then either you made a mistake or they're not inverses of each other. Okay? So, let's take a look at verifying with an example here. So let's verify that f and g are inverses given f of x is x cubed minus 1. Okay, and we'll say g of x is the cube root of x plus 1. Okay, so we'll do one together here. So we'll do this one together. So let's find f of g of x here. So you can see again, aha, we talked about composition of functions yesterday because we're going to be talking about inverses today. And so we really need those composition, right? We want to be comfortable with evaluating composition of functions in order to, verify things are inverses of each other here. So f of g of x, that means we're going to do f of cube root of x plus 1. Okay, so we're going to take that cube root of x plus 1, we're going to plug it in for the x. Okay, it's in the f there. So we end up with then the quantity cube root of x plus 1 cubed minus 1. Okay. And then we simplify this, right? So cubing a cube root, what happens? Cancels out. And so we have x plus 1 minus 1. The plus 1 and minus 1 cancel, and we're left with just x. So, aha, check. So these two functions are inverses, right? Oh, no, Mr. Wade, you got to check the other one. So you guys are going to do that right now, okay? So go ahead, do g of f of x. See if you also get x that way. Okay, yes. Yeah, go ahead, Hayden. All that baguette makes you thirsty, huh? Yes, Renike. That's fine, but I want you to just be able to recognize that it does. You can simplify it further if you need to, because that's kind of like that looks more foreign, I would say, than this. This looks like, oh yeah, this is quadratic, but maybe we're using fractions like that. Yeah, understood. But yes, you may leave it like that. Give you a few more seconds here to finish up. Okay. Hopefully you got that. X. So now can we say these functions are inverses?
Yes.
Silent nod. Yes, 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 yes. Exactly right. We can. Okay. So these are inverses of one another. Okay. All right. So that's one way to show two things are inverses by using algebra there. Okay. The alternative method of showing inverses is graphically. Okay. Inverses also relate in how they look by their graphs. So we can also verify inverses graphically as well. Okay. If two functions are inverses, their graphs are reflections over the line y equals x. Wow, that's way far out there. Okay, there we go. If two functions are inverses, then their graphs are reflections over the line y equals x. Okay? So, I'm going to show you that here with a graphing calculator, right? Let me maybe pick something more interesting here. I'll start with f of x equals 2x cubed minus 1, and then I'll go ahead and give us the inverse 2 of f, and we'll say it's going to be the cube root of x plus 1 all over 2. Okay, like that. So we'll graph this here on our graphing calculator and see this kind of what I mean by the reflection over the line y equals x. So first of all, understand the line y equals x, right? That is a linear equation. We can graph this by hand, right? The slope of this is 1, the y-intercept is 0, and so it's going to be like kind of a diagonal line that goes through the origin with a slope of 1. Okay? So what I'm going to do is I'm going to graph, let's see if I can get this all to fit at once. Okay, that's not that bad. I'm going to graph the 2x to the third minus 1, and I'll also graph the cube root. Now, you can do cube root a couple different ways here. Maybe the most straightforward way is you press math. The cube root command is right there, number 4 in the math. All right, and then again, when you type this in, be careful. Put parentheses around the numerator, because otherwise you might not get the right graph there. You can put parentheses around the denominator. It's not necessary. So there's only one thing in it, but definitely put parentheses around the numerator. Okay, like so. I have that nice pretty type on my calculator, math print. Okay. Unfortunately, if you have a TI-83 model that includes the TI-83 Plus or just a TI-83, you can't get this kind of type. If you have a TI-84 and your calculator doesn't have that ability, I think I can actually give that ability to your calculator if you'd like. That's something I can do later. Okay, so I can upgrade your operating system so that you can have that on your TI-84 calculator. Okay. So anyway, if that's something you want. Anywho, so there are they, and we're also there are those the two functions there, and we're also going to graph the line y equals x, so that way we can see, that line of reflection there. All right, so there's our cubic. There's its inverse, and there's the line y equals x. Okay, now it's a little bit hard to maybe not, maybe you're okay with it being this way, but it doesn't quite look like they're reflections of each other, right? It's not quite right. Part of the issue here is the way the screen is, right? Okay, so the screen is wider than it is tall, and so, but what we're graphing here is from -10 to 10 and from -10 to 10. So the -10 to 10 this way is more stretched out as opposed to the -10 to 10 this way, which is more compressed because of the fact we're graphing on a rectangular screen. If you want to fix that, though, if you press the zoom button and go down to zoom square, okay, it will adjust. It will kind of adjust the x-axis so that way it doesn't have that stretch. It kind of makes it now, I don't know, the right scale or something like that. And now maybe it's a little bit easier to see that reflection there. Okay, you can see that certainly if we were to reflect this over that line y equals x, we'd end up with that right there. Okay, so there's graphically how we can kind of verify that. Okay, we could do the same thing if we wanted to back with those the lines that we calculated, right? Back in the first part of our notes where we talked about like the line 2x plus 6 and the line 1/2 x minus 3. Let me do it this way. Okay, there's the one line. There's its inverse, and there's line y equals x. And again, you can easily see that kind of reflection right there, right? And so here's what I want to talk about, though. I told you I wanted to come back to this function and the inverse that we calculated right here. Okay, if we look at that, okay, so 1/2 x squared plus 3/2. There's the one. There's the other one, and there's line y equals x. Okay. We have a problem. Okay. The original function that we had, which is this, okay, that's that square root of 2x minus 3. If we reflect that over the line y equals x, are we going to get this graph? We are not. Okay, we aren't. So, are these two things exact inverses of one another? The answer is no. How do we fix this? How do we remedy this, right? Do we just say, well, it's close enough? Okay. Well, this piece of our graph right here, this square root, it will reflect to some of this graph, right? This piece right here is going to reflect to here. Okay, and so the way we can kind of account for this, going back to our original problem here, is to restrict this problem's domain. How can we restrict the domain of this parabola so that it would reflect to this part right here? Obviously, if we say the domain for this parabola is all real numbers, the issue there is going to be that we're going to include, this piece right here. So what should we restrict the domain to be? Yes. 0 to infinity, including the 0. Exactly right. So here we want to say, comma, x greater than or equal to 0, or 0 to infinity. Oops, and I accidentally didn't include that there. Okay? X greater than or equal to 0, or 0 to infinity. Okay? To now make sure that those things match up. Okay? Now, let me go one more step back here, and let's talk about that original function whose inverse we were trying to calculate. What is the range? What is the range? And I'll just highlight it here, so that way you don't have to even worry about. I'll make it a little bit easier for us here. Let me just graph that. What's the range for this function? I hear it, right? 0 to infinity, is it not, right? So, or we could say y is greater than or equal to 0 is the range. Or we could say that it's, again, the range is 0 to infinity. Right? Now notice here, the range of this function, how does that compare to the domain of its inverse? It's the same. What do we do when we find inverses? We swap what? The x and y's. So the domain of this will swap to be the range of this, and the range of this will swap to be the domain of this. Okay, again, if these functions are inverses of each other. And that all comes from that idea of swapping the x's and the y's, right? Same idea, too, if you remember back from geometry, and maybe you don't because it's been a while, okay? But this is why also we have, when two functions are inverses, their graphs are reflections over the line y equals x. When you reflect over the line y equals x, all you're doing is swapping x and y values, okay? So it's all connected to this idea of swapping x's and y's, okay? So that's important to remember there, okay? That's important to remember there. And this leads us into this idea of, being able to swap the x and y's and stuff like that. Okay, this leads us into another kind of descriptive property that we have here, okay, which is the idea of 1, 2, 1. Okay, a function is 1-to-1 if its inverse is also a function. Now, if I give you the graph of something, and I want you to tell me, is this thing a function? What's the test that we use for that? Vertical line test, right? Okay. Well, if we use a vertical line test to determine if a graph is a function or not, what kind of test could we use to determine if an inverse, a horizontal line? Because what is a vertical line? When you reflect it over a line y equals x, it becomes horizontal. And so then to determine if a function, when you reflect it over that line y equals x, is going to remain a function, you use the horizontal line test. Okay, so the horizontal line test and again, I don't have a very pretty way of writing this, but we'll just say it anyway. So if a horizontal line passes through two or more points of a function f, then f inverse is not a function. Oops, I went off the screen. This is so shit. There we go. All right, so let me show you some examples of what I mean by that. So I'll just graph a line, and let's just say, hypothetically, this is like y equals 4x minus 5. Okay. Is this line, is this a function? Does it pass the vertical line test? Yes. Okay. Does it pass the horizontal line test? Yes. Okay. So is this line 1-to-1? Yes. The line is 1-to-1. Okay. Again, this phrase 1-to-1, okay, it has its meaning in the idea of how x's and y values are paired together. One x value goes to exactly one y value. Okay? Any x value you select is paired with exactly one y value. Any y value you select is paired with exactly one x value on this line. Compare that to a parabola. Is it a function? Yes. Is it 1-to-1? No, it doesn't pass the horizontal line test, right? For example, right here, I'll just draw like a... Okay. Why is it not 1-to-1? Because we have this one y value that's paired with how many x values? It's got two x values it's paired with, right? Both this x value and this x value will yield this one single y value. So it's not 1-to-1, okay? Here we've got, I guess you could say 2-to-1, right? Two x values paired to one y value, okay? And so it's not 1-to-1, okay? And in fact, if we were to reflect this, right, you would have something that's not a function. It would look something kind of like, like that. If I can do a quick and dirty sketch there. All right, that's the idea. Okay. So, not 1-to-1. Okay. So that's the idea there. Okay. All these things are related to one another in that sense. Okay. Questions on anything so far? Any questions on any of that? Yes, Sid.
I have
Why does it matter if it's a one-to-one? So that's a good question, right? So for our purposes, we typically work with functions, right? Like we typically want to work with functions, and it can be, I guess, kind of troublesome sometimes if you plug a number in and you have like two possible answers. You know, sometimes you just want to get kind of like your one answer, so to speak, or one thing to match with it. So it will matter more later when we talk about like trig functions, right? So do you remember trigonometry a little bit, right? Okay, so if I'll just briefly here, real quick, just show you what I mean by that. So for example, let's talk about sine. Sine is going to look something like this, right? But then keep going and then keep going kind of thing, right? So talking about sine of x, well, we also have sine inverse, right, or arc sine, the inverse trigonometric functions. We want to be able to evaluate those. The problem is, though, when we talk about inverse trig, well, now you're going to have an infinite, this thing's not going to be a function anymore because you're going to have these, well, if I keep going, obviously, the values will overlap. We're going to have, the horizontal line test is going to fail like several locations and stuff like that. And so what we end up having to do then, we want to create, so we limit our domain to create a one-to-one relationship, so that way when we evaluate inverse trig, we only end up with like one answer as opposed to having like multiple answers and stuff like that. So it's just mostly just kind of help with evaluation and stuff like that later. And it'll help, again, when we get into those kind of more tricky things. Right now, what we're working at is so simple. It's kind of like just preparation, really, for something that we're going to see later. So that's all. So, yes? So when you are describing a function's inverse, you want to be describing it in such a way that they are inverses, and so domain restriction may be an important maybe something to consider if you need to do that. So I didn't really give you a straight up answer there. I think most of the stuff we're going to be dealing with right off the bat, like early on right here, the domain restrictions won't be necessary. We'll like make them kind of straightforward, kind of easy. But as we move on, it's going to be important. It will be important, yeah. But for right now, I think it's going to be okay without domain restrictions. I think you'll be okay without having to worry about it. Just know that they're a thing, and that something we're going to maybe need to do in the future when it comes to making our graphs match up and stuff. Okay? Any other questions? All right. So then your assignment is on the Google Classroom. Then I don't have any more I want to show you today. Okay. So let's see. I can put up on the board though for you too, if you don't want to have to get your Chromebooks out or anything. Okay. So page 98. Numbers 19 to 21. 49, 51, 54, 59. Please only do part A for those. Okay, and then also 107. Okay? So that's your homework right there. Yes.
Want me to like show you?
Yeah, if you want to get that out, I'd like to take a look at that.
I don't know how to like upside or anything.
Oh, you submitted already? Okay, well then if that's the case, you won't be able to get back into it. But if it happens in the future, if it happens in the future, don't worry about submitting it. Bring it in. We can then fix it or whatever. Answer all the other questions that you can, obviously, and then.
There was like it was the one where I was like the plotting one.